this video, we're going to walk through the introduction to Chapter 2, focusing on functions and graphing. I'm going to read through these notes relatively quickly just to save time. They're also available for you on the portal. But we're going to highlight and focus on functions, and here's the good starting point, is to say, what is a function? Well, a function is nothing more than a rule. We'll also call it a relation. And this rule assigns to each input element x in an input set. X is what comes into our function. Assigns to each element in an input set exactly one element called f of x as output. We put x into our function, we get f of x as output from the function. We'll talk about domain and range extensively in this unit. The domain is the set of all input values that go into our function. It's all the x elements. And the range will be the set of all output values, all our y elements or f of x elements that the function produces. And so as a basic starting point, here's a function. F of x equals the square root of x minus 1. If we were going to describe that function in words, we'd say we take our value of x, we subtract 1 from it, and after we've done that subtraction, we then take that result and compute the square root of it. If we drew a machine, x comes into the machine, we subtract 1 from x, figure out what that value is, take the square root of that, we've produced our output f of x. If you're asked to evaluate a function, how do you do that? It's a plug and play. F of 5. I'm going to go ahead and do what? Plug 5 in for x. So I'm going to have f of 5. There's my 5 in. I'm supposed to subtract 1. I get 4. And then I'm supposed to do what? Take the square root of it. The square root of 4 is 2. 122. That's my input value. Subtract 1. Get 121. Take square root. F of x for x equals 122 produces an answer of 11. F of 122 equals 11. F of 26 over 25. Take 26 over 25, subtract 1, which is the same as subtracting 25 over 25. I wind up with 1/25 that I have to compute the square root of, and I walk out with 1/5. So that's functions, basic rules. How to evaluate a function. Nothing more than plug and play. We're going to deal in section 2.2 with something you saw in Algebra 2 last year, piecewise functions. And this is a function such as the example here, g of x, where our output value is based upon, and what rule we follow for our output value is based upon the value of our input. And so here I have g of x equals 5 whenever my input value is 2 or less than or equal to 2. And if I get a value that's bigger than 2, if x is greater than 2, I'm going to work and solve the function g of x using 2x minus 3. I've highlighted these in red and blue just to kind of help me identify the different pieces. And down here, I'm asked to evaluate the function at a series of input values. You'll see 3 of them in red. Why? Because -3 is less than 2. 0 is less than 2. And by the way, the value of 2 is less than or equal to 2. All 3 of these input values live in the, what I'll call the red part of the function. All those input values are less than or equal to 2. And so as a result, they'll spit out an output value in each case of 5. When I do an input value of 5, as you see here, well, I live in the blue part of this function. I plug in 5 into 2x minus 3, 2 times 5 minus 3, 10 minus 3. G of 5 is equal to 7 on this piecewise function. We're going to do a lot with piecewise functions as we roll forward in section 2.2. Moving forward, another section we're going to see, section 2.4, talks about the average rate of change and net change. Net change is nothing more than taking 2 input values and seeing how much change have I gotten in my output value. So it's nothing more when you look at a problem like this to find the net change in the function. Just let us know the difference in the output value from the one input to the other input. What different function results did they produce? So I have a function here, h of t equals t squared plus 5. And I'm asked to compute the net change in this function from t equals -3 to t equals 6. Well, how do I do it? Evaluate h of 3, evaluate h of 6, take those 2 answers, h of 6 minus h of -3, and compute it. Over here, h of -3, -3 squared, which will become 9 plus 5, 14. H of 6, take 6 in, square it, 36, plus 5, I get 41. My first input value produced output of 14. My second produced output of 41. What's the net change? Nothing more than 41 minus 14, and I just don't have a pen to complete this out, but that would be equal to 27. So net change, all you need to do, evaluate the function at 2 points, compute the difference in the output values, and you have nailed the net change that you're requested to solve for. Now, next piece in chapter 2, we're going to focus on function graphing as well. And a key point, all the functions are real. No imaginary numbers, no complex stuff that's going to happen here. All input, all output values, all independent variables, x, all output values, y, are always going to be real numbers. And as such, we'll be able to graph them on the x and y scale. And one of the things we're going to be asked to do is evaluate where functions have acceptable domains. Identify the domain of each function. Hopefully, all real numbers would work, but sometimes we're going to run into problems or situations where we can't have any value, any real number work with our function. And you're going to see some examples down here. The first is one certainly you saw in Algebra 2, I expect, where you have a rational function. And you know in a rational function, your denominator cannot be equal to 0. When I look here, 1 over x minus 3 times x plus 2, I realize that if x is equal to 3, or if I set x equal to negative 2, this denominator is going to be equal to 0, and this function is undefined. It can't live. So how can I handle this? How do I identify the domain? Verbally, I could say it's all real numbers except for x not equal to 3 and negative 2. And that's what you see here, x, semicolon. There's the real number symbol, that funny barred R. And then what do I list after that comma? The values of x that cannot be taken on. X can be all real numbers except it can't be 3 or negative 2. And if I use interval notation, I write that same thing as negative infinity to negative 2, union negative 2 to 3, and union 3 to 0. That shows all the values in what we call interval notation, all real numbers, because you can see negative infinity to infinity, and then we have a couple breaks. We can't be equal to negative 2, we can't be equal to positive 3. That's how we handle that in interval notation. We'll also see a problem like this where our function is the square root of, in this case, 4 minus x. Remember, real numbers only. You can only take the square root of a positive number or 0. You cannot take the square root of a negative number and produce a real number answer. As a result, I know that 4 minus x has to be greater than or equal to 0. If I move x over to the other side, I would be saying 4 is greater than x. And just to write that inequality in a little bit better shape, I'm going to say x is less than or equal to 4. And here it is in interval notation. I run from negative infinity all the way to 4. And notice that I have a solid bracket here because I can achieve the value of 4. Now our last problem does a little bit of extra work. Here's our final example. H of t equals t plus 1 divided by the square root of t plus 7. Now, this adds a couple additional wrinkles to some of the things we already look for, and I've started to put it out here. When I look at the square root of t plus 7, I kind of recall from my first piece that I cannot what? Cannot have t plus 7 be a negative number. So my starting point, I say t plus 7 greater than or equal to 0. However, in this particular circumstance, what do I know? My denominator cannot be equal to 0. So I know that t plus 7 is not allowed to be equal to 0. I need to meet these conditions. And what's that translate into? When all is said and done, I need t plus 7 to be, in this case, a positive number. And that tells me that t better be what? Greater than negative 7. So t greater than negative 7. Sorry, that looks like a 7 again. T has to be greater than negative 7. And if I'm going to write that in interval notation, I would go with the following. I'll just put it over here. I've got a little bit of arm room. T greater than negative 7, I write negative 7, open parentheses, and infinity. Every value from negative 7 to infinity is acceptable. I'll be able to work with this function. A negative square root certainly can't work. And again, in this particular instance, because the square root of t plus 7 is in the denominator, it's not allowed to be equal to 0. And there's my final piece. I have to be greater than negative 7. So this is the final example here in this piece. We have one more section just to talk about from a graphing standpoint, and we'll pick up with that in one moment. In this unit, you're going to be responsible for knowing a series of functions that we're going to call parent functions, and they're listed on the next 2 pages. There's the identity function, y equals x, which simply says whatever value of x you put in, that's the same thing of y that comes out. That looks like a nice 45-degree line. The absolute value function is a special type of function that always returns a positive number. So if I put in -9 into the absolute value function, I return positive 9. If I put in -1, I return positive 1. So the absolute value looks like a V shape. And what I'd like to do very quickly on the calculator, I'd like to show you how do you go ahead and put that in to your calculator to graph it. So I'm going to go to my y1, and some of you might have already seen this, but to get to the absolute value function, do the following. Hit your second, and then hit your catalog button. And the first function that comes up for you is actually the absolute value function. Choose that. And what your calculator now has done is put ABS with parentheses around it. So I could do absolute value of x, close your parenthesis, and now I can go ahead and graph that. And there's my good old V shape. So again, remember, second, catalog, you'll choose the absolute function, absolute value, you'll get your parentheses, just go ahead and put in what are you trying to take the absolute value of, close the parentheses, and you're good to go. The squaring function is our good old parabola, y equals x squared. We're pretty familiar with that. I'm not going to spend much time on it. The square root function, remember, you can only take the square root of what? A number that is 0 or greater. As a result, you get a restricted domain. The domain for this function is what? X is greater than or equal to 0, or in interval notation, 0 with a bracket up to infinity with parentheses. Always you can remember, what does the square root function look like? Well, if my thumb is just the x-axis, my finger bent like that is a good representation of what the square root function looks like. 2 more functions for you to be aware of. One is the cubing function. Again, we filled in some values on the table. You can run these through on your calculator. And the cube root function, which is just essentially a transformation. If you look at it, it almost looks like that thing has kind of been flipped and rotated. Cubing function to get the cube root function, very, very similar characteristics when you consider that there's a transformed rotation. More on that down the road. The last piece I want you to make sure you're aware of is interval notation. We use English language inequality or statement language on the left-hand side, translate that into interval notation on the right side. Remember, when you have equality in interval notation, that's going to be represented by a bracket. When you have inequality, always represented by a parenthesis. Sometimes your domain or your interval is going to be split up. If that's the case, use the union operator as we discussed before. The union operator shows you the different pieces of your domain or the interval that you're trying to define. X not equal to 1. Notice what we've done. You run from negative infinity all the way up to the value of 1 with parentheses to show that you don't touch that. You now have to what? Well, you got to continue for every value that is greater than 1, and that's what the second piece of this interval does. Negative infinity to 1, open parenthesis, union, 1, open parenthesis, to infinity. And similar, here's an example where I have x not equal to 2, x not equal to 4. I now have a couple, if you want to say, holes in my interval. And again, just handle that by unions. So that's our introduction to this particular section, the intro to chapter 2. Hope this gives you a good start for what you'll be looking into work with on this unit.